Okay, so I will start today's lecture. So far we learned how to use the PyTorch library for implementing the deep learning architecture. And from now on, I will explain about more computer vision-like techniques such as segmentation, pose estimation, and also subsequently I will teach how to implement object detection algorithm. Okay. By the way, we don't have any midterm exam, right? And also during the midterm period, we don't have any class. Okay. And this is computer vision applications we have seen in our introductory classes. And this is the semantic segmentation task. Okay, so image classification, it classifies images according to their main object. But there has been, strong assumptions that the images have to have one main object in image classification task. So there's some limitations. So in object detection task, we try to recognize the multiple object with the bounding box representation, but this has some limitations. So in semantic segmentation, we want to reveal pixel-wise the boundaries for each object from the whole image. That's the semantic segmentation algorithm. So we will today learn about how to implement this using the deep architectures. And also the other important application in computer vision is estimating some of the pose of the hand or the human body. So the task is aiming to reconstruct some of the pose representation like this or this kind of mesh from the RGB image. So this pose is composed of, for the hand, we define 21 key points. So 4 points on each finger. And also because we are having 5 fingers, there are 20 points. And 1 point is coming from the wrist. So there are a total 21 key points predefined. And our aim here is to estimate their 3D coordinate, the XYZ coordinate of each key point. So because we are estimating XYZ coordinate for each landmark, so this is definitely the regression task. And we have to estimate 63-dimensional vector. So this is this number comes from this. So we have to reveal XYZ coordinate for 21 key points. So we have to estimate 63-dimensional vector from the network when estimating this kind of pose. Okay. And human body, from the human body, we also define similar topology for human body. So we define normally 17 to 20 something, 25 maybe key point from the human body, and we estimate their XYZ coordinate for each landmark. And also this kind of thing is the mesh representation. Here it seems like smooth surface, but it has indeed this number of vertices in this mesh surface. And by connecting 3 vertices, by regarding 3 vertices as one face, we define smooth surfaces from this number of vertices. So, because there are too many vertices on this mesh, it seems like smooth, but it is not smooth indeed. It is discretized by this number of vertices. Okay, and also in the human body, we need around 6,800 vertices on these human meshes. Here this number of mesh vertices are defined, and by connecting 3 vertices, we call that as triangular face because we are actually connecting 3 vertices. This is triangle. So we call this as the triangular phase. We define this kind of phase by connecting three vertices together, and that is visible like this, like the smooth surfaces. That's the mesh representation. Anyways, but I mean, either this kind of key point or this kind of mesh, the thing we have to estimate is their vertices XYZ coordinate. Okay. So anyways, this is a regression task, and I will teach today how we can achieve this kind of pose estimation using the deep architectures. So the first thing is the semantic segmentation task. So as I told you, in the semantic segmentation task, we have to label each pixel in the image with a category label, okay? So I mean, here, for example, from this kind of RGB image, we have to pixel-wisely reveal their semantic classes. Okay, so these regions are tree regions, and this is the cat region, and so on. Okay, and this is same, right? I mean, the naive way to implement this kind of semantic segmentation algorithm is just using this kind of sliding window approach. We call this as the sliding window because we will slide this sized window around the images. And then when the window is located here, we crop those patch and then apply this type of CNN to by inputting this patch, by resizing this patch to fit to the input of this deep architecture, and we apply the feed forward algorithm on this patch, okay? And then in the last part of the deep architecture, we will get some of the probability, okay, for the semantic class, okay? So in that way, we can classify each patch, okay, using, image classification method, okay? This is the naive way to extend the, image classification algorithm towards the semantic segmentation algorithm. But the problem is, it takes a lot of time. So for example, if there are this amount of pixels in the images, this is normal image size. So the width is 640, and the height is 480. This is a kind of normal image size. But sometimes we also deal with this kind of HD, high definition image, which may have this number of pixels within it, or even we are also having ultra HD images nowadays. So even it has even more pixels within it. So if we have this amount of pixels, then we anyways have to apply this kind of CNN H multiplied by W times. Okay. We need H multiplied by W CNN operations while achieving the semantic segmentation map using the deep architecture, okay? But it takes a lot of time. And also even CNN has a lot of parameters. Even it requires the GPU to make it parallelized, to make it efficient, okay? So, it takes a lot of time already for one CNN operation, but if it require this amount of operations when achieving one semantic segmentation map, it may take like a few hours, maybe 5 hours to get one semantic segmentation map from the deep architecture. So the thing I want to say is this is not efficient and this is not practical, okay? So, if it takes 5 hours to get one semantic segmentation map using the AI algorithm, then it is bad. It might be better for us to, label it by human hand. Okay, it is not practical. So the computer vision researchers have to search for the efficient way to make the deep architectures work for the semantic segmentation algorithm. Okay. So and they try to think about this kind of architecture. That directly input this type of input images and directly estimate this type of semantic segmentation map rather than apply this type of deep architectures on each small patch. The researchers are begin to think about this kind of architecture that input the entire image and then output once this type of semantic segmentation map. Okay. So you can see this is the input images dimension H by W. This is height and width by 3 channels. Because this is the RGB image, it has this kind of dimension. But in the output, the semantic segmentation map, it will have just one channel. Okay. It will have some of the integer index. For example, this is cow. So in this region, it will have integer 1. And from this region, that is the tree region, and it will have integer 2. This would be integer 3. Sky would be integer 4. Okay. Their output is denoting some semantic classes, and they are actually the integer. Okay. And actually, it requires just one channel to represent this kind of thing. Okay. Anyways, if we have this kind of architecture that can input this dimensional array and can output this dimensional output array, then we can achieve this kind of thing more efficiently rather than apply deep architectures using this kind of small patches. Okay. Maybe this first part can be achieved by the CNN, to say convolutional 2D operations we already learned. Okay, so by inputting 2D, we can differentiably process the images to make it into some of the feature representation. Okay. So by applying this kind of convolutional operations. But the problem is how to enlarge the features into, the original image scale. That was the question. Okay. But the computer vision researchers have found this type of transposed convolution operation. Okay. And I will show the characteristic of this transposed convolution operation. So convolution operation, as we already learned, if this blue are image pixels and the gray regions are filter, then when we apply filter in this region, what we will do is multiply the filter coefficients and the image pixels in the element-wise manner. And by adding them, we get one output pixel here. Okay, and then we will shift the window to the right, and then do the same to get this subsequent output pixel. And we do this by moving the windows by this manner. Okay. The transpose convolution operation will do the same. Okay, so these gray things are also the filter. Okay, so if it is located here, the thing we will do is same as before, same as the convolution operation. So also the blue region that is representing the input Okay, input response is represented as the blue. And I mean, these pixel values are all zero, okay? I mean, they are zero padded, okay? And the thing happened here is same as the convolution operation. So if filter is located here, then the filter coefficients and also the image pixel values are element wisely multiplied and added to make this output pixel. Okay, so the core operation of transpose convolution is same as the that of the convolution operation. Okay, but the detail is having some difference. And also you can again see they are mainly composed of these two types of operation, the addition and multiplication. Okay, so by combining the input using this operation, we will get the output of this transpose convolution operation. In that sense, this transpose convolution operation is differentiable. Okay, I already told you that every polynomials are differentiable. So I mean, polynomials are mostly composed of plus, minus, multiplication, and division. Okay, so their output is differentiable with respect to their input. Okay, and because this transpose convolution is also composed of addition and multiplication, that this operation is also differentiable. But the other characteristic that we are requiring is it has to enlarge the input signals by applying this transpose convolution operation. But it indeed does that kind of thing. So I will detail how transpose convolution is working. So this red part is the how to say the input images, and this green is the filter coefficient, the 2x2 filter corner, okay? And we will see how it will work when the stride is 1. And let's say the input image, it is the 5x5 dimensional signal, okay? Then by default, what we will do is we apply 1 zero padding by default. Even though we specify we will not use any zero padding, it by default, it applies 1 zero padding around the images. So this is the obtained images by applying 1 zero padding, okay? And then what we will do is applying this filter corner one by one to calculate this each output pixels by shifting these windows by 1 pixels. Because our stride is 1, we will move the windows by 1 pixel, okay? So, I mean, if the input is 5x5 dimensional array, by applying this 2x2 corner, you can see we can obtain this 6x6 dimensional array as our output. And indeed, the output dimension is becoming larger than the input signal, okay? So the transpose convolution is tending to produce the larger dimensional output signal compared to the input signals, okay? And the other characteristic of the transpose convolution is if their stride is set as 2, what they do is let's say the input signal is 3x3. What they do is they become to have some offsets in this input signal. Okay, so the pixel values of the original input image is located like this. Okay, and then apply 1 zero padding around these enlarged images, and then apply this 2x2 corner on this region to get each output. Okay, are you guys following this? And because we are enlarging the offsets between each pixels of the original image, the output images are tending to more enlarged compared to the input image. Okay, so let's say if the input image is 3 by 3 array, the output array, their dimension is 6 by 6 when we use the stride 2. Okay, I mean the concept of stride is slightly different from that of the convolution operation, right? So in the convolution operation, the stride is meaning how the offset, the window is shifted. But here in transpose convolution, the stride is meaning the offsets between input pixels, okay? So because of this, when we use the transpose convolution, we can get enlarged signals, okay? And also it is differentiable, so that operation could be used in this type of network that can enlarge the feature vector obtained in the middle layers. And the other characteristic is if we apply padding, then it also has somehow different meaning to opposite meaning compared to the convolution operation in this transpose convolution. So let's say the input image is 3 by 3 and 2 by 2 corner, and let's say we are using the stride 2, then this is same as before, okay, making this type of enlarged input, that is same. But thing is, if we use padding, if we set the padding parameter as 1, then actually this is meaning that removing the outer pixels, okay? So that's why we are at last having this type of signals rather than this, okay? In the convolution, if we set padding larger than 0, then that means adding some 0 pixels around the input image. But in the transpose convolution, it has actually the opposite meaning. It removes the boundary pixels, okay? And then we apply this 2 by 2 corner in this manner, and we'll get this type of output, okay? So, you can feel like that this transpose convolution is having different characteristic to the original convolution operation, and that is tending to enlarge the original signals, okay? But maybe you are curious about why this kind of operation is called as transposed convolution, okay? This is the original convolution operation. So this is the input image, and this is the corner. Then we will apply filter corner in this manner. And from here, by multiplying each coefficients and input pixels element-wise manner, we will get this type of output pixel, okay? And by shifting windows by 1 pixel to the right, and we will get this. And by applying the filter corner here and here, we will get these two values. That is how original convolution operation works. But this type of sequential process could be implemented as the matrix multiplication in the PC, okay? When implementing this convolution operation in your code, you will maybe implement that in this way. So first, we will make this kind of convolution matrix by extending this corner, 3 by 3 corner. Using some rules, we can make this type of convolution matrix. And also, we will flatten the original input image, whose dimension is 4 by 4, into 16 by 1 dimensional vector, okay? And the convolution operation could be represented as the matrix multiplication. that can be framed as the multiplication of this convolutional matrix with the flattened input signal, okay? Then you will get this type of 4x1 dimensional vector. But if you reorganize, reshape this one-dimensional vector into square, then these values is actually same as this output value. Okay, so indeed, this convolution operation is implemented as this type of matrix multiplication inside the code. But the thing is, in the transpose convolution operation, this convolution matrix is actually transposed. So, I mean, in linear algebra, you may learn about this kind of transposed operation, okay? So it will switch the width and height of this array, okay? I mean, this transposed means the same thing here. So it will transpose the convolution matrix. So previously it has wider width than the height, but because we transpose it, it has wider height than the, than the width, okay? It is transposed, okay? And if we multiply the input signal with this transposed convolution matrix, then you may get this type of output, okay? And you can see now, when the input size is 2x2, the output size is now 4x4. It is meaning that we are actually upsampling the input signals, okay? And by rearranging this one-dimensional vector into square, we can get the final output. So this is why the transpose convolution is called as transpose convolution, and this type of characteristics is also, happening due to this characteristic. Okay. So this type of networks, we can implement it by involving the convolutional 2D operation similar to the CNN networks, and combining with some of the nonlinear layers and some of the pooling layers here, okay, to constitute this type of feature extractor. And subsequently, we use the transposed convolution operation to upsampling it to original dimensional signal. Okay, so are you guys following this? And then after making this architecture, the thing we have to do is first make some data set, okay, the X and Y pair, okay, the input and ground truth pair. For given this kind of RGB image, we have to make a lot of this semantic segmentation label Y, okay, we have to manually label maybe. And then we will update the parameters of this network we just defined. Initially, this network will have some random parameter, so their output might be noise, okay? It will not properly predict the semantic classes for each pixel, but when given this data set, and by applying the 5 lines of code we learned, okay? The gradient descent algorithm to update this parameter sector. This parameter sector is updated to predict the semantic segmentation map that is close to their ground truth, okay? So by making this kind of differentiable architecture that can upsample the intermediate feature, and then we can actually train that to make it make their output close to our ground truth that we define. Okay. Are you guys following this? Okay. And this is actually the example code to implement the semantic segmentation algorithm. So we normally call this type of architecture as the encoder-decoder architecture. So the first part is called as the encoder. The later part is usually called as the decoder. Okay, so encoding means in computer vision context, encoding means making the input image into the feature. And then decoding means, transforming that features into the output. That is usually called as the decoding process. So, encoder is indeed making the input image into the feature, and the decoder is indeed transforming the feature to the output image. Okay, so that is called as the encoder-decoder architecture, and this is actually the class we already learned. Okay, so here we can define our encoder and decoder architecture, and we will stack several layers for the encoder, and you can see we indeed stack convolutional 2D operations and some of the nonlinear layers in between. And also in the decoder, you can see we stack multiple transpose convolutional operation. Actually, this is the grammar for loading the transposed convolution operation in PyTorch. So you can just use this, okay? And anyways, we can just stack multiple transpose convolution operation, to decode the features, okay? And this is the fourth function. You can, if this is, the input image X is, inputted, we first apply the encoder and then apply decoder and return the output signal. Okay. So this is the encoder-decoder implementation of the encoder-decoder architecture. And using this, you can, also using the same training code we already learned, okay? And using some collected data set for the semantic segmentation task, we can learn this encoder-decoder architecture, okay? Maybe this is the example code for training this encoder-decoder architecture, okay? Okay. So you can see we actually use the same training code as before, okay? And also I will explain about the image generation tasks as well. So, we already learned about this type of segmentator, okay, that can output the same dimensional signal from the input images. But the thing is, as I told you, the output of this segmentation map would be this type of integers, okay? Even though our output is two-dimensional signal, but their values, actual values are integer, okay? If there are 20 classes, then the values will have this type of numbers, integer numbers inside. And when you see this type of architecture, you will also think that you can also estimate some of the RGB images from the output. You can think about outputting some of the RGB images from the network. So for example, this is the encoder-decoder architecture. Let's think about some of the case. Your input to this network is image, RGB image, and also the case, your output is also having the same dimension as the original image, okay? Actually, this task is dealing with such cases. So you can, if you are curious about the details, then you can also follow, this reference, okay? What they do is, they have this type of input image, but on purpose, they delete these center patches, okay? And the thing they want to achieve is inputting this type of RGB image, wanting to estimate the erased region, okay, to recover this kind of images. Okay, are you guys understanding this? Okay, so these regions are actually estimated from this network. So you can now think about this type of architecture. Okay, I mean, this is actually the result from this paper, and I mean, you can see that actually the AI is generating some of the image patches. Okay, and these two are both from the algorithm proposed in this paper, and you can see these patches are robustly actually reconstructed. And this is the result by the human artist. There is some discrepancy between the reconstructed patch and the original context image. But this here, it has less discrepancy between the context region and also the reconstructed patch. Okay? Actually, this task is called as the in-painting. Okay, but in general, this is estimating the original images. Okay, so I mean, as I told you, this type of network, the encoder-decoder architecture, can be used to train this kind of, I mean, to achieve this kind of task. Okay, so I mean, given image, in this task, securing the XY data is very easy. So when you have original image, you can delete this region patches, okay? And this becomes the Y data, and this center erased, images are becoming the input X, okay? So securing data, it is very easy in this type of application. Anyways, you make the architecture and you secure the data. Then the last thing is using some of the loss function, and you can train the encoder-decoder architecture to generate the erased part. Okay. So indeed, the loss is the mean square error loss is used for this task. Okay. But the thing is, when you do only use the L2 loss, this paper is saying that the estimated pixels is becoming blurred. Okay. I mean, this is because as I told you, in the image segmentation task, the pixel values are limited to the number of classes, and their space is, rather small. Okay, so the quality of the semantic segmentation output is, non-problematic before when achieving this semantic segmentation task. But when you try to estimate the images itself from the network, each pixel values now have 0 to 255 values. Okay, even they have 3 channels for each pixel. Okay, so you can now feel like that the features, the space of this RGB is a lot wider than that of the semantic segmentation output. Okay, that's why actually this output is becoming blurred. Okay, so when you naively use the L2 loss, which is the mean square error loss, when training this type of encoder-decoder architecture, then the output signal might be not in the high quality. Okay, so here, what they actually added is the adversarial loss. Okay, I will briefly introduce this. Okay, so if you use both L2 loss combined with this adversarial loss, then this paper is saying that the quality of the patches is becoming more and more better, okay? Becoming better. And this is adversarial rules. This was very important previously, but now this is also becoming very old paper. So the original concept is coming from the GAN paper. Maybe you already heard about this generative adversarial network proposed in NIPS 2014. But now, I mean, this is very important basics for the the generative AI. But nowadays, the generative AI is mostly using the diffusion network rather than this GAN. So, I mean, previously, GAN is prevailed, and knowing this kind of concept was very important. But nowadays, I mean, diffusion is actually prevailed the GAN algorithm. So this is not that important, but I mean, this is worth knowing anyways. So I will tell you what this adversarial loss is meaning. Okay, so I mean, adversarial loss is actually wanting to train this type of generator. Okay, so generator is actually composed of the transposed convolutional operation we just learned. Okay, so what they do is they input some one-dimensional vector. Actually, we normally input some random noise to here, and they generate two-dimensional images. Okay, from the one-dimensional vector, we will generate some 2D images. That's what generator is doing. Actually, that's what decoder side is same as what decoder side is doing. Okay. So, anyways, I mean, this will not be in any exams or any other assignment, but I think this is worth knowing. So that's why I'm telling this. Okay. I mean, if you are only interested in getting good scores in this lecture, then you don't have to pay attention to this, maybe, yeah. But anyways, I will explain that for maybe 5 minutes. Anyways, this is the generator. I will call this as the G, and this is the discriminator. I will call this as the D network. Okay, and this generator will make the image, and we will call this as the fake sample because it is generated by some network and it was not pre-exist in the real world. We will call that as the fake sample, okay? But we already have some real images, okay? This is our training data. So we will call those kind of real world images taken by our camera as the real image, okay? And what discriminator is doing is, it is actually the binary classifier, okay? Given the images, either from fake image or real image, it will tell that the images are generated or pre-existing images, okay? We will call the pre-existing images as the real samples, okay? So for the images taken by camera as the real, and the discriminator wanting to tell that as real, and for the generated images, it wants to call that as the fake, okay? So this is the, I mean, explanation for some of the terms here, okay? But what these adversarial loads wanting to achieve is this kind of thing. So discriminator, you can think that as the policeman, and generator, you can think that as the fake money generator, okay? it generates some fake money, but this discriminator wanting to discriminate the real money from the fake money this generator is making. Okay, so generator is this is actually network having some parameter sector, and for discriminator, this is also the network having some parameter sector too. Okay, these two networks are both trained. Okay, their parameters are both trained, but I mean, how they are trained is discriminator that is wanting to say this as the fake data and this as the real data. So that is actually trained to achieve the binary classification. And this generator is trained to deceive this policeman. I mean, even though it generates some fake data, uh, it wanting to achieve, I mean, it wanting to deceive this discriminator to say that the money it generates as real, okay? So this is very important part. So generator what is trained to deceive this discriminator to say its output as real, okay? So that's the training objective, and that's actually contained in this single formula. So this discriminator is denoted as D, and generator is denoted as this G, okay? And I mean, we use these adversarial laws because while fighting against each other, the quality of this generator is becoming close to the real data, okay? So their fake data, they are generating fake data, but it is mathematically proven that by additionally having this discriminator that can discriminate their fakeness, the quality of the generator, their output quality becomes close to the real data. It is mathematically proven, actually. And I will explain a little bit about this formulation. Okay, so this real data, you can call that as X. Okay, and fake data, you can call that as Z. Okay, and I will call the fake as 0 and the real as 1. Then this is the loss function, okay? And actually for this loss function, we will maximize this term, this entire term in the aspect of the discriminator, and we will minimize this loss for the generator. Okay, so, and we will first minimize these terms for the generator, okay? And then we will maximize those terms again for the discriminator, okay? So first, I will explain how to minimize this term for the G. Okay, so, sorry. I will first explain about how to maximize this for the D. We will first maximize this for D and then apply min G. Okay, so we have to do this first. Okay, and when minimizing this loss in the aspect of D, then I will first draw this type of graph. Okay. Again, this is the log function. This is the log function, and here it should be 0, 1. okay? And this X is the real input image. And this is sampled from the real data distribution. So you can think this as the, this is meaning that X is sampled from the real data distribution. And this is actually the loss function using X, okay? So if you input X, the real data, to D, okay, to this discriminator, then their loss function looks like this. And you have to actually maximize this loss for, for D, okay? So, and also I already told that D of X is the binary classifier whose output would be bounded to 0 to 1, okay? If its value is larger than 0.5, we will regard it as the 1. And if the output is less than 0.5, then we will regard this as the class 0. So that's the binary classifier. So, so their dx, their values are bounded to this region, okay? And actually, we have to maximize this loss function, within this range, okay? So it means we will make this value, because this is the direction to maximize the values on this graph. So by maximizing this graph in this range, we will get this point, okay? Which means dx would be close to, this is 1,0. So by maximizing this loss in this range, dx will be close to 1, okay? It means this loss function is meaning that when the real sample X is coming to D network, discriminator network, the D network will estimate it as class 1, okay, which is the real class, okay? When X is inputted to D, then it output it as the real sample. And the opposite thing is meaning that, I will draw the graph here, okay? And this is the log. And it would be like this, 1,0, the same graph, okay? The x-axis is denoting this, so it would be the same graph. And we have to actually maximize this for Z samples. So Z is meaning the fake samples, and they are following this type of fake sample distribution. So when Z is inputted to the generator, then this is meaning some of the fake samples generated by the generator. And if we input the generated samples to the D network, indeed, it have to say it as the 0, okay? I will show that. So, we have to maximize this value, okay? And again, this value is bounded to this region. And to maximize this, these values, entire values have to be close to 1, okay? To maximize this graph in this region, it have to close to here, close to this point. And it is meaning that this value have to be close to 1, okay? That is meaning this. And actually, this value have to close to 0, okay? So when this is meaning that by maximizing this loss for the fake sample Z, DGG, that should go to 0. That means that when we input the generated samples to the discriminator, it will become to output 0. Okay, so 0 means the fake sample. Okay, this is actually meaning that when we input X to the real sample X to the discriminator, it become to say it is the real sample. And if we input Z to the G network and make the fake sample and input those sample to the discriminator, then discriminator have to say it as the fake sample. Okay, that's the maximum part, okay, of this loss. Then I will tell you about this minimum part. Okay, so now we have to minimize this loss for G network, but this term doesn't have any G variable, so we can just omit this. Okay, and we will only minimize this part. Okay, and I will draw the same graph here, log. Okay, and here 1 minus. Okay, and this is 1, 0 again. And for minimizing this, when these X values are bounded to this region, we have to minimize this value by making it towards here. And this is actually meaning that we will make this value to here. Okay, so that is meaning that we will make this value as 1. So when you interpret this, then it is meaning that G network, and also you have to note that when applying minimum G, D is fixed, which means D will be constant. Okay, D will be regarded as constant. And also when applying max D, G network will be freeze, which means G will be regarded as constant. Okay. Anyways, D is now fixed. Okay, but we only want to minimize the loss function for G. Okay. So this is meaning that given fixed discriminator, when you generate some fake data and input it to the freeze discriminator, then discriminator will say it as real sample. Okay, actually this is meaning that deceiving discriminator. Okay. So I mean, this is fake sample, and discriminator is trained to say those fake sample as fake, but the generator is now trained to deceive this discriminator. Okay, so this is a bit difficult to understand. So I mean, if you do not understand this, then also I mean this will not be in any quiz or exam or assignment, so you can skip this part as well. Okay, but I'm explaining this because this is kind of important concept in general in AI. So yeah, that's why I'm telling this. Anyways, this simple formula is having two concepts: training discriminator to say fake samples as fake and real samples as real. But at the same time, by minimizing the same formula for G, we can train G to make some samples which is very close to the real sample. Okay. So now this is the encoder-decoder architecture. And this is the input image you already seen, having, erasing the center patches. And this is the, erased patch. This would be Y, and this is the X input. And so we can apply the L2 loss for this encoder-decoder architecture, we can close to their Y value. At the same time, we will apply this type of adversarial laws, okay, to the output patches. So we can think this encoder-decoder architecture, the entire encoder-decoder architecture as the generator in here, okay? And having another discriminator network and apply adversarial laws we just learned here. Then this generator is struggling to deceive this discriminator network. And as a result, their quality is becoming better than before. I mean, better than merely using L2 losses, okay? So that's why previously I'm telling this. I mean, when you merely use L2 loss, which is the mean square error loss, okay, then the quality of the patch would be blurred. But if you additionally use this type of adversarial loss combined with L2 loss, then the quality is becoming better, okay? That's actually told in this paper. Okay, so I mean, this is happening because the RGB image space, their pixel value space is actually larger than the semantic segmentation, their maps space. So this kind of, issue is becoming. So that adversarial loss could be a solution to relieve this. And now is almost time, but I want to just introduce this part. So pose estimation, I already told you from the RGB image, we want to reconstruct some of the coordinate values of the predefined landmark point, okay? So here we define this type of 14 joint from the human images and want to estimate their XY coordinate. So sometimes we include Z, but sometimes we don't include that, okay? Anyways, this is the pose estimation task. And the naive way to implement this pose estimation network is just involving the CNN network. And yeah, of course, their input is this kind of RGB image, but their output is now multi-dimensional vector. So because I'm telling you that there are 14 joints, so and also we will estimate their XY values. So now we have to estimate this dimensional vector. Okay, this is now the regression task. Okay, so this would become the Y. Okay, and this would become the X. So using the same training code, okay, and using the same CNN maybe, you can train this CNN to estimate now this type of XY coordinate, okay? So you can achieve post estimation in that way, okay? And I will show you more details in the maybe next class, okay? So for today, let's finish here and see you next Monday. Thank you.